Research Center and Department of Physics in Indian Institute of Science, Bangalore. He completed his PhD from IIT Kanpur, and during his postdoctoral studies, he helped initiate a paradigm shift in NMR by inventing 2D spectroscopy with Professor Richard Ernst and Professor Kurt Wuthrich. Both of them won Nobel Prizes later. Professor Richard Ernst, he passed away very recently. And then in late 1990s, Professor Anil Kumar, he started working on experimental realization of quantum computation using coupled nuclear spin networks, which are weakly coupled to the environment, so they have long coherence time. So Professor Anil Kumar and his group helped realize many quantum gates and showed novel ways to create like pseudo-pure state, implementing various algorithms and other quantum games. And I was very fortunate to have done my PhD under his supervision. We all worked on quantum dynamics, either on relaxation or on quantum information processing. And Anil has been extremely prolific. He is very active even now, although he is well past his formal age of retirement. And then he got numerous accolades and awards. He served as the president of Magnetic Resonance Society for many years. He is fellow of all Indian national academies, and he is a fellow of Third World Academy of Sciences. He is a Rajaramanna fellow. And his students, we are all spread over India in institutes of national importance, TIFR, IISERs, NISERs, and others. So it's really great to have him here in QIQT. And he will show us how one can manipulate nuclear spin networks to help realize, quantum information processing, quantum computation. And with that, sir, I invite you to begin your presentation. And to the audience here, I give you Anil.
Thank you very much, Ranjit. Thank you for a very kind introduction. So I'm going to basically introduce the subject of quantum information processing by NMR. And the question that I'm saying, why and how? And that's what I intend to convey. Please just stop me in the way if you have any question. If it's a long answer, I will ask you to defer it later. Otherwise, if I can answer quickly, I will answer right away. I'm at the Indian Institute of Science, Bangalore. I'm an Emeritus scientist of INSA at the moment. And I'm grateful to Indian Science for giving me the opportunity for learning science in a free way. Okay, I introduced the NMR, the phenomenon. The magnet and the magnetic moment given by, I'm using my cursor. Maybe I should use.
We can see your cursor. Your cursor is very much visible.
Visible?
Yeah, it is visible. Yes.
No, is it visible clearly?
Yeah, it's visible.
Okay.
Your cursor is now close to H equal to minus mu dot B.
So interaction energy between the magnet and the magnetic moment, magnetic field is given by minus mu dot B. For nuclei, mu is gamma h cross I, and if you apply a magnetic field in z direction, then the interaction energy becomes minus gamma h cross I z B naught. For spin half nuclei, either can be either plus or minus half, and so we have the degeneracy is lifted in the magnetic field, in the plus half and minus half, with the energy gap of gamma h cross B naught, which is called h cross omega naught, which is the Larmor frequency. Okay, and so omega naught is the Larmor frequency is equal to gamma B naught. The most commonly studied nucleus is the nucleus hydrogen proton. Its resonance frequency in a magnetic field of 2.35 Tesla or 23.5 kilogauss is 100 megahertz. Other spin half nuclei are fluorine 19, whose resonance frequency in the same magnetic field is 94 megahertz, and carbon 13, which is 1.1% abundant, is 25 megahertz. NMR was first detected by Bloch in Stanford and Purcell at Harvard in 1945. Their papers are separated by 100 pages in the same issue of Physical Review. for which they shared the 1952 Nobel Prize. So NMR has, as far as I'm concerned, three major applications: structures of biomolecules in solution, MRI, and quantum computing. Although quantum computing is not as big as these other two, but for me, I'm going to, they have more or less equal value. So let me just look at the structure of biomolecules in solution by NMR. And a single experiment that I did in 1979-80 in the joint project with Dietrich and Ernst is the two-dimensional NOE experiment, which has tremendous information about the structures of the protein. For example, each cross-peak here identifies as proportional to some distance between this proton and this proton. So every cross-peak has information about the distance between those two protons. And once, so you can also classify the intensity of those peaks into strong, medium, and weak, and attach distance constraints like 2.2 angstroms, 2.5 angstroms, 5 angstroms, and feed this information into what's called
recording in progress.
Okay, a distance geometry algorithm, and it gives you a structure of the protein. The interesting part is that this paper is co-authored by two future Nobel laureates.
Recording stopped.
Okay, and so this was a very important development in the structural determination of biomolecules by NMR. For this work, for development of 1- and 2-dimensional Fourier transform NMR, Richard Ernst got a 1991 chemistry Nobel Prize. He was not very happy that Dietrich did not share the prize with him. Anyway, he got it all alone, but very recently we lost him. Dietrich had to wait another 11 years to get his chemistry Nobel in 2002. So the second major application of NMR is MRI. In fact, now it's the MRI is so popular that NMR is identified as MRI. And so this is the first Fourier 2D MRI experiment that I happened to do in Ernst's lab in 1975. Paul Lauterbur had done CW NMR and showed the image of two tubes of water, and we did by Fourier 2D. This is the first Fourier 2D experiment, and by this simple experiment, we demonstrated two tubes of water capillaries in a NMR 5 millimeter NMR sample tube, and this experiment is known as KWE experiment for imaging. This was also the first 2D NMR experiment. We wrote software ab initio for doing 2D calculations. Image quality after 1990 had improved to the point that MRI was going to stay. And the Nobel Prize for Physiology and Medicine in 2003 for MRI was given to Paul Lauterbur and Peter Mansfield. Peter Mansfield played a very important role by using repeatedly using the magnetization from different planes, and so that it would be much faster. And so he rightly shared the Nobel Prize. Why I am emphasizing this dates here is because it took a long time to award the Nobel Prize to Peter Mansfield, because there was another gentleman who was creating trouble. His name is forgetting right now, and he said he gave the first idea and he should share the Nobel Prize. In fact, when this Nobel Prize was announced, he took out full page advertisement in New York Times and Washington Post saying Nobel Committee has done this justice and he should be given the prize. Of course, Nobel Committee never corrects itself. So that's why the problem was that therefore the Nobel Prize to Paul Lauterbach was getting delayed, and finally the Nobel Committee did not want another controversy, and so in 2003 they gave him the Nobel Prize, and he was not well, and he passed away in 2007. MRI has revolutionized human radiology. Every one of you are familiar with this in a common man on the street and understands MRI, and it's hailed as a major contribution of science to humanity. With this introduction to NMR, I now come to quantum computing, and let's say another dimension of NMR. Okay, all present-day computers, you can call them classical computers, use binary logic, 0, 1. In fact, this picture that you see on the screen has all zeros and ones only. Okay, and all computations follow from this yes/no answer. And Feynman in 1982 suggested that it might be possible to simulate the evolution of quantum systems efficiently using a quantum simulator. He never talked about computing, quantum computing. He wanted to do simulation. Okay, so what is so special about quantum systems which is not there in our classical systems? In bits have 0, 1, but qubits, a classical bit can have either 0 or 1, but a quantum bit, we call it qubit, can have both 0 and 1 simultaneously with different amounts of coefficients. So this is, while a classical bit has just 2 possibilities, a quantum bit has infinite number of possibilities. And you see, this creates a new opportunity to do a lot more work than just a classical bit can do. Okay, you see the difference that they have very large large space to cover with this quantum bit. The other important property of quantum systems is entanglement. You can create states, 2 particle states, which are not resolvable into tensor products of individual particles, like you cannot write like this. Such states are called entangled states. This is also known as EPR state. And these entangled states are used in quantum computation and teleportation and many algorithms. So this is what is so special about quantum systems, which doesn't exist in classical cases. Of course, to make use of is the top of my slide hidden? Is the top of my slide hidden?
Yeah, we can see that. I mean, it's the quantum algorithm slide that you are showing.
Okay,
Yes.
okay. Because the strip here is covering my slide, but it doesn't matter. It's not covering your slide, huh?
No. We can see everything on the full slide.
Okay, all right. So now to make use of these quantum properties of the qubits, one has to write new algorithms. Okay. For example, the first algorithm that came up with the Shor's algorithm in 1994 is a prime factorization. It's a very important problem because our communications are secured by the fact that you can't classically, if you want to find prime factors of a large digit, it is not possible to do with the classical computers. But if you use quantum algorithm, Shor gave an algorithm in 1994, these scale exponentially, and this scale logarithmically, and that's a big difference. So if you could build as powerful a quantum computer as classical computer, the same speed, then this can factorize 400 digit in 3 years. And so your bank accounts, etc., are safe because of this reason that you cannot classically find prime factorization of large numbers. And military secrets, communication secrets are all dependent on this factor. Then Grover, a graduate of IIT Delhi, while working in Bell Labs, and in his spare time, came out for a search algorithm for quantum systems. Classically, if you want to do a search in unsorted database, it needs of the order of n by 2 operations. But if you go over search algorithm, which use coherent superposition, then you need of the order of root n operations. And this becomes important if n is of the order of million, not when it's order of 100. Another algorithm is the distinguish between constant and balanced functions. Certain functions are either constant or balanced. Classically, it needs several steps. Joshua algorithm, even like 1992, can distinguish them in a single step. By 2009, Seth Lloyd and team had come up with a solving quantum algorithm for linear system of equations with exponential speed up. So these are the various algorithms one can use, quantum algorithms. Of course, every experimental technique is trying to find the best quantum computer, trapped ions, which are very high, far ahead of others, was trapped ions, polarized photons, cavity quantum electrodynamics, quantum dots, very highly rated possibilities, cold atoms, somewhat harder, and NMR. But the experimental technique that has made biggest development is Josephson junction qubits. Okay, they are also trying to do Fullerene-based ESR quantum computer, but at the moment, Josephson junction qubits are the far ahead of everybody else. And in physics, Nobel Prize for quantum experimental quantum computing was given by 2012 for trapped ions to David Weinfeld and Sergei Harosh for QED. I don't want to read this because I think Nobel Committee was too fast in giving a Nobel Prize for experimental techniques of quantum computing, because there are other techniques which are now more promising than these. All right. Well, we actually ended up into this quantum computing using NMR purely accidentally. We were trying to, my student Kavita Durai, who is now Professor Naida Pune, was trying to play in the spin dynamics and invert zero quantum coherence. And we published a paper inverting zero quantum coherence, and it turned out that David Corey called it a swap gate. I'll come to it. And so we were forced to start this work because we were working in spin space and found that these are gates. This story I'll give fully. All right, nuclear magnetic resonance. Nuclear spins have small magnetic moment and behave as tiny quantum magnets. When placed in a magnetic field, spin-half nuclei orient either along the field or opposite to the field. A transverse radio frequency field tuned to the lambda frequency of the spins can cause transition from 0 to 1. That's a NOT gate by 180-degree pulse. We never called it a NOT gate. We called it a 180-degree pulse for 50 years of NMR. But it's a NOT gate. Then or can put them in coherent superposition by 90-degree pulse. We have been applying a 90-degree pulse ever since NMR was discovered. We never called it a NMR gate. We called it causes coherent superposition. Okay, so these are single qubit gates. But spins are coupled to each other by indirect spin coupling, and controlled NOT gate operation can be performed using J coupling, multi-qubit gates. So nuclear spins are qubits. Of course, one requires high magnetic field and very high stability of the magnetic field of the order of 1 part in 10 to the power 9, 1 ppb. I will show you why we need this soon, but it turns out that such kind of magnets were needed for protein structure determination, and we did not need to buy any new hardware to do quantum computing. We use the same hardware as was being used for protein NMR research. And so this is the NMR Research Center in its heydays. We had a 300 megahertz, 700 megahertz, 500 megahertz, and 400 megahertz, which these are the resonance frequencies, these are corresponding magnetic field. And these are superconducting magnets. So why NMR? A major requirement of a quantum computer is that the core, and this happens. Nuclear spin half nuclei liquids retain coherence to hundreds of milliseconds, and their longitudinal state for several seconds. What I mean is the T1, the T2 is hundreds of milliseconds, one is several seconds, and this we know for sure for spin half nuclei this is true. And so this is one reason why NMR is a good idea to use for quantum computing. A system of n-coupled spins form an n-quantum computer. And unity transforms can be applied using radio frequency pulses and coupling. Various logical operations in quantum algorithms can be implemented. Addressability problem in NMR sample tube, we have the order of 10 to the power 18 spins. Do we have 10 to the power 18 qubits? No, because all the spins cannot be individually addressed. Someday it may happen, but at the moment we cannot address them individually. The progress so far is that spins having different Lama frequencies can be addressed in the frequency space domain, resulting in as many qubits as Lama frequencies, each having 10 to the power 18 spins. So what we are doing is, we are doing ensemble computing, we are not doing individual particle computing. And that's very big drawback of NMR. Okay, so please remember this. We're not addressing individual spins, then we are working only in the ensemble space. Of course, one needs unequal couplings between spins, yielding resolved transitions in a multiplet in order to code information as qubits. So let me introduce some NMR qubits to you. This is a very good sample, and we have used it many times because the gate time is inversely proportional to the coupling. So larger is the coupling, smaller is the gate time. And this particular system has very large couplings. The proton-proton couplings are small, but this is a one bond fluorine carbon. This carbon is actually enriched by chemistry, chemical means, and then and proton. So there is a 3-qubit system: carbon 13, proton, and fluorine. Bromine nucleus gets decoupled because it has spin 3/2, and it's a quadrupolar nucleus and has a fast self-relaxation, and it gets decoupled from other spin half nuclei, and we get sharp proton, carbon 13, and fluorine NMR spectra. And we have used them many times to do experiments. Homonuclear spins having different chemical shifts. Gamma frequencies also form multi-qubit system. The chemical shift comes from different chemical environment. For example, this proton have a chemical shift of the order of 80 hertz because this functional group is different from this functional group. And so this proton and this proton resonate at about 80 hertz difference. There are 5 hertz coupling, which shows up as splitting. And so this is a 2-qubit system. And the line width of 0.5 hertz. And this is why we need a ppb homogeneity in the magnet. 1 qubit is chloroform, not C13, 12 proton, 0, 1. You have 1 line. Here it's 4 lines. And here are 12 lines. For 3-qubit system, this molecule has 3 chemical shifts, about hundreds of hertz away, and couplings of tens of hertz. And so we have a 3-qubit system, 2-qubit system, and 1-qubit system. Here, in the all proton-proton system. We call them homonuclear spins. Now, pure states are in high demand in NMR QC, in QC, and we also try to do this in NMR. And so the requirement of pure state is trace rho is equal to trace rho square is equal to 1. For a diagonal density matrix, this condition requires that all energy levels except one have zero populations. Such a state is difficult to create in NMR. You can create in optics, but not in NMR. So David Corey of MIT came up with a nice excuse, and he called it pseudo-pure states. Okay, so what he did was he expanded the density matrix under high temperature approximation and retained the first order term here. All others are much smaller anyway. And so when you apply, where alpha is of the order 10 to the power 5, and you apply unitary transform on this rho, this gets transmitted to delta rho, and because U inverse is 1, and so we create a state in which all levels except one have equal populations. Such a state mimics a pure state. That's a statement from David Corey. And that's very important because that allows us to use NMR for quantum computing. Okay, let's take a two-spin system. So the density matrix will have 10 to the power 5 plus delta rho, which is of the order of the Boltzmann distribution. 2, 1, that's equilibrium. But actually it is population is 2 plus 10 to the power 5, a million, 2 plus million, 1 plus million, 1 plus million, a million. We take out the million or 10 to the power 5. And this is the deviation population from uniform background. Okay, I can also write delta rho equal to IZ1 plus IZ2. It's 1, 0, 0, minus 1. We add 1 to it, it becomes 0, 1, 1, 2. And that's 0. 0. So all these numbers go back to ground state, then it's a pseudo-pure state. So all the populations are transferred to the ground state, and this is a pseudo-pure state. This is an equilibrium state, and this is a pseudo-pure state. Now, so you can also say that delta rho is equal to IZ1 plus IZ2 plus 2 IZ1 IZ2, and if you plug it in, it comes to 4, 0, 0, 0. Equilibrium density matrix is IZ1 plus IZ2, which is 2, 1, 1, 0. I mean, you add 1 to it, it becomes 0, 1, 1, 2. That one that I've added is cheated from this 10 to the power 5. So this is equilibrium density matrix. This is pseudo-pure state. Okay. Now how to go from here to here? There are several ways one can do methods of preparation pseudo-pure state. David Corey himself came up with this idea of spatial averaging, and this still continues to be the most useful and usable method. And I'll show you several occasions where we have used spatial averaging. Logical labeling, Gershenfeld came up with this in studies. We used to show experimentally that this worked. Temporal averaging was Knill, and this, what was his name? Chinese Chuang, who factorized 15 to 5 and 3 and got CNN news and used temporal averaging. Whereas pseudo-pure state, PM Fung did this. Especially average logical labeling technique was given by somebody else, but expertly was shown by Mahesh for the first time. Using long-lived singlet states, SS Roy, while working with Mahesh, created these. Let's look at spatial averaging, Corey's method. Okay, most commonly used method. We have an equilibrium density matrix at IZ1 plus IZ2, okay? And we apply a certain number of pulses and evolution under J coupling and refocusing using pi pulses. And you have to then write down all the steps at what is at 1, 2, 3, 4, and I have not written them down. I have written down the state at the end, IZ1 plus IZ2 plus 2 IZ1 IZ2, and this is the gradient pulses which destroy any X and Y magnetization or X and Y operators here. And this also makes this a non-unitary operation. So if you want to go from the equilibrium state to a pseudo-pure state, you have to apply some non-unitary operations or vice versa also. Okay, so these are our non-unitary operations. These are gradient pulses which destroy X, residual X and Y magnetizations at 1 and at 5. Okay, I don't have this calculation with me, but you can try to practice yourself and see, reach this goal, starting from Z1 by spin 2 pi by 3 X pulse. You get certain operation, throw away the XY components and only the Z, then come here and then allow J coupling evolution into this, and then see whether you can reach this yourself or not. A tutorial will be very useful, and Ranjit can certainly help you with that. This is the Gershfeld had done what's called a special, what's this called? My hidden slide is cut. Oh.
We can see your slide. Your slide is totally
logical labeling. Logical labeling.
Yeah, logical. Yeah, this is logical labeling.
Logical labeling method. So look at the energy level diagram of a two-spin system. This is the equilibrium population 4, 3, 3, 3, 2, 2, 2, 1. Okay, divided into two subsystems in which first qubit in state 0, and in this first qubit in state 1. So it's just arranged in such a way that it looks like subsystem states. Okay, and so then you apply these two pi pulses, interchange the population of this 2 here and 3 here, and 2 here and 3 here. It will look like this. Okay, this is subsystem pseudo-pure state. This is pseudo-pure state, and this is another pseudo-pure state. This is subsystem pseudo-pure state. This was described by Gershfeld in Science in 1997, experimental Kavita in 2000, and here is the experiment. So this is the equilibrium spectrum. Here is the spectrum of the pseudo-pure state. I don't details of show you how it looks like, but you can satisfy yourself that first spin, this is second spin transition. Oops. Okay. For example, this is the third spin. This is the second spin transition, and this is the first spin transition. Okay, all are 1, 1, 1, but their positive, negative depends on this. For example, when you go to this one, it's negative. This population is bigger than this one. Okay. Temporal averaging, Kneel use this. So what he did was he did 3 experiments, starting with equilibrium population distribution, this population distribution by interchanging these two, and this population by interchanging these two, and carried out a full calculation, and then in the end, assuming that he has done no nonlinear operation, he added the result. So it looked like as if he had started from here, which is a pseudo-pure state. Okay, that's a neat idea, but I personally think it's too much work. Okay, here the pseudo-pure state by especially average logical labeling technique. It's more or less, this is the equilibrium spectrum, this is the spectrum of I naught, and then you apply this pulse and you create subsystem pseudo-pure state. But this is 2, 1, 1, 1, and this is 1, 2, 2, 2. So this ensures you that you have subsystems to appreciate. But these are just created at a time thinking that we might use them, but we have never used subsystems to states. We have created them, but we never use them. Let's look at some quantum gates by NMR. Okay. For example, a control NOT gate. A control NOT gate, if we want to use the qubit selective pulses, that is, we apply a pulse on full spin 1 and spin 2. This is the correct way of doing things. Okay. So you go from I1Z to I2Z to I1Z to I1Z, or you use, we used transistor selective pulses. A control NOT gate in which the control is the first qubit and the result is in the second qubit. So the pi pulse here is a control NOT gate. Okay. And so, and this is done with the qubit selective pulses, that is spin selective pulses. This is transistor selective pulses. Okay. It's very important to do it this way because you can put this in a circuit. You can't put this in a circuit. You can only demonstrate that you're putting, for example, a NOT gate, sorry. NOT gate. NOT gate is just a pi pulse on spin 1. Okay. And in spin selective pulses, we apply also not pi pulse on spin 1. A swap gate. It's a complicated operation on qubit selective pulses, but it is straightforward here. You apply a pi pulse here, a pi pulse here, and back a pi pulse here. And actually, Kavita had done this to show that you can invert zero quantum coherence. And we published a paper showing we can invert a zero quantum coherence using these pulses. A few months later, I got a paper from Corey saying this is a swap gate and use this method. So then we said, oh, well, we can do swap gate without our realizing it. And we started our work in quantum computing by NMR. Toffoli gate is control NOT gate. And it's very easy to do this in a transition selective pulses, control on first 2 qubits, result in the third bit. So we get a control NOT. But to do the control NOT with qubit selective pulses, it's a lot of hard work. And you have to come up with a pulse sequence, which is not straightforward. Here are the experimental results. The NOT on 1, obviously, you invert the spin 1. Okay, here is the equilibrium spectrum. Sorry, I didn't show you this equilibrium spectrum. And then we invert this, so NOT on 1, control NOT on 2, and control NOT on 1. Okay, so here you invert this one. Okay. Swap gate. And using transistor property. Okay. So the equilibrium population is this. P1, P2, P3, P4, pi pulse here, pi pulse here, and back a pi pulse here. You get back P1, P4 remain the same, and P2, P3 get interchanged. So this is a swap gate. 0, 1 goes to 1, 0. Okay, when we try to do this in a homonuclear spin system, at equilibrium, P2 and P3 are equal. So if we do this swap gate, we will get the same spectrum as a normal equilibrium spectrum. So how to convince referee that we have done something? We first change the population of one of these control NOT operation, and then a swap gate. And then you can show that you have done the swap gate. Okay. The Toffoli gate, experimentally, we have done it only by using transition selective pulses. That is control NOT gate. Control NOT. Control on these two, third and third. So this is just a pi pulse on this transition. It's easy to do with using transition selective pulses. Okay. This is an interesting slide. So Richard Earls, who never liked the idea of doing quantum computing by NMR, nevertheless published one paper showing that he had earlier given this pulse sequence of 2D NMR as preparation pulse, evolution method, evolution mixing and detection. He had called these periods for 2D NMR. He renamed them as creation of initial states, labeling of the initial state, computation, and reading the output state. And we faithfully followed him and did some 2D gates. But you have to use one of the spins as a labeling spin. Okay, so the labels on this spin are the other two spins are in state 0, 0, 0, 1, 1, 0, and they are all the first spin transitions. But other spins are in this state. I don't know whether I'm communicating with you or not. I should have put an energy level diagram here, and that would have made it easier to see. Okay. Yeah, word I have written. Transitions of I0 are labeled by the states of the I1 and I2. And here, this is a very interesting story. One fine day, sitting in a lab, and Mahesh, I'm sorry, Arvind and Kavita were sitting in my office, and Mahesh came and put this paper in front of me, saying is a complete set of 24 reversible one-to-one qubit gates. He never asked me that what he's doing. He just, without asking me, see, we have a group, everybody talking to each other. And then he went ahead and did all these experiments. And he said, it's a complete set. Arvind only said, how do you claim it's a complete set? He said, 4 into 3 into 2 is 24. And Arvind said, yes, fine, I agree. What it meant was, in the first 4 possibilities, once you have fixed this, then there are 3 possibilities, then we have fixed these 2, there are 2 possibilities and 1 possibility. 4 into 3 into 2 is 24. So this is a no operation gate, not 1. Not on the 1, so 1, 1 will become 0, 1. 1, 1 will become 0, 1. 0, 0. Okay. And this is a home exercise for all of you. Go and check any mistake. Okay, if you can find out, please let me know. Already how many 20 years have passed, nobody has found things. This is the gate. 1, 1 remains 1, 1. 0, 0 remains 0, 0. 1, 0 goes to 0, 1. 0, 1 goes to 1, 0. This is a famous stop gate. Okay. And so this was great fun. See, qubit 2D gates. This is no operation gate. This is no operation gate, nothing can be done. So everything remains normal, not on 1 to fully or not. And the system is this one. It has 2 protons and 2 fluorines. Fluorine also spin half. And so this is the fluorine spectrum. This is also fluorine spectrum, I think. And this is the proton spectrum. There each has a 8 lines. Nice qubit system, 3 qubit system. Okay, now I was talking to you about gates. We have not utilized coherent superposition. Now the quantum algorithm which utilize coherent superposition, there are 2 of them I will talk to, DJ and Grover's subtle algorithm.
Sir, there is a question on quantum algorithm. Long back, I think Chandramani Bhatts, he asked how quantum algorithms are generated. What are the mathematical operations used for generation of any quantum algorithm? I did not ask this question on his behalf. I was waiting till you reach quantum algorithm part. So
yes, that's correct. There's no other answer. Yeah, right. That's correct.
Right. So would you like to comment on that? Like, I mean, how these algorithms are generated?
Yeah, you have to look for a problem that can be used, can be solved by quantum algorithms.
Right.
Okay.
So it basically the problem prompts the algorithm.
Yeah.
Okay. Thank you, sir. Okay.
All right.
Yeah.
And before describing coherent superposition, I will do some algebra. Okay. The Hamiltonian for a two-spin system is given by mu1 IZ1. That's the Raman frequency, the first spin, Raman frequency, second spin, and coupling between the two. If the chemical shift difference between these two is large compared to J, this Hamiltonian is reduced to a simpler form, IZ1, IZ2, IZ1, IZ2. Under this condition, the product states are eigenstates of the above Hamiltonian, and they are alpha alpha, alpha beta, beta alpha, and beta beta. And you can write the energy levels as to half mu1 plus half mu2 plus 1 by 4j minus 1 by 4j minus 1 by 4j minus mu1 minus mu2. And the resonance frequencies are 1 minus 3 is mu1 plus half j, 2 minus 4 is mu1 minus half j, and so on. So we have mu1, which has two lines split by j coupling, and mu2 is two lines split by j coupling. Okay, and the states of the other spin. So it is the first spin transition with the other spin being state beta. This is the first spin transition, other spin being in state alpha. What I mean is this one. This transition is the first spin transition alpha to beta, but the second spin is in state beta. Okay, here is a one spin, first spin transition. Sorry. First spin transition, and the other spin is state alpha. Okay. This is alpha beta, alpha alpha. And so this is how you calculate the spectrum. Population coherence in density matrix. So the density matrix is given by psi1 star, psi1, product psi1, psi2, sample average. In NMR, we do not detect individual spins, but observe an ensemble of spin variety in the system. These are described by a density matrix defined as psi1 psi, and expand that psi to AI, Ci, AI, and so you get rho ij, AI, aj, sum over ij. That's the density matrix. For a two-spin system, A alpha plus B beta, and we get a density matrix as A star, A B star, A star B, B B star, ensemble average. This ensemble average is missing here in this. Please substitute a bar here. What's happening? Okay. Diagonal elements of population or diagonal elements of coherences. Under equilibrium condition, this coherence average is 0, and we have A star and B star, which is population P1, P2 of the two levels. Expectation value and equation of motion. The expectation value of any operator is given by trace of rho with R. The equation of motion of the density matrix derived from Schrodinger equation is given by d rho by dt minus I h rho conductor. The time for time independent h, it has a very simple solution. Rho t is equal to e to the power minus I h t, rho 0 is equal to I h t. And we generally try to use this facility to make some simple solutions. Even if you have a time dependent h, we break it up into discrete steps of constant h, and then calculate the evolution. I'm sure you're familiar with this very simple idea of going around time dependent functions. Equilibrium density matrix in partition function. Equilibrium density matrix is given by e to the minus h plus kt. Under high temperature approximation, it reduces to this, and this reduces the trace, which is n. So equilibrium density practice is proportional to 1 by n, 1 minus beta Iz. At room temperature, we have 10 power 5 plus 1 and 0 population. And the net magnetization is m naught, given by b naught gamma h cross QT. And beta is of the order 10 minus 5 for NMR. Now we apply radio frequency field to detect NMR signal. We apply RF field perpendicular B naught field, say along x-axis, frequency omega of the order of omega naught. The Hamiltonian of the RF field is given by 2 gamma B1 Ix cos omega t. This is an oscillatory field. We break it up into 2 counter-rotating parts. And in the rotating frame transformation, we get gamma h B1 Ix plus Ix e to the power 2 omega t. The counter-rotating part is neglected, it's far away. And we left with HRF, rotating frame RF omega 1 Ix. The total effective Hamiltonian in the rotating frame is given by omega naught omega minus omega naught Iz plus omega 1 Ix. And so it looks like as if we have it offset when we apply a radio frequency field of strength omega 1 at offset delta omega, which is effective field is in this direction. If omega 1 is much greater than delta omega, then along the x-axis. Unity transfer RF Hamiltonian is given by U is equal to by EIHRF RT. There should be a bracket here somewhere. Okay, it's by omega 1 Ix T, so e to the power I theta Ix, theta is equal to omega 1 T. And so the unity transform associated with RF Hamiltonian is given by cos theta Ix plus I sin theta Ix. Cos theta Ix gets expanded for a spin half using property of Ix squared equal to 1 by 4. We get cos theta by 2, and sin theta Ix, we get 2Ix sin theta by 2. Okay, and so RF, the unit transform associated with RF in the X field is cos theta by 2 unit plus 2Ix I sin theta by 2. But theta equal to omega 1 T. Oh, this is no meaning. And your RFY is given by this. So single qubit gates, U naught is equal to this, theta is equal to pi, and U naught acting on a state, U 1 0 1 single spin gets 1 0. You can calculate 1 0 1 0. U naught acting on a density matrix, P1 P2, P2 P1 invert. So we invert them. Okay. So whatever information I've given you by pictorial argument is now here by mathematics. The same thing. Hadamard gate. U is equal to 1 plus 2Ix Iy. This is the matrix of the Hadamard gate. You perhaps are familiar with it. Otherwise, this is a very important matrix. Okay, and the Hadamard matrix is acting on a state. This put them in coherent superposition. Acting on a density matrix, it creates coherent superposition between eigenstates 0 and 1. So 0 Hadamard gives you 0 plus 1. 1 Hadamard gives you 0 minus 1. The Hadamard pulse sequence is pi by 2 y by x, and you get the Hadamard matrix. Here is the Hadamard matrix. Sorry. Phase shift gate. It's phi z is equal to phi pi by 2 pi x minus this, and get phase shift E to the I phi. Spin echo. This was described by Erwin Hahn in 1952. It is one of the most important steps in NMR and quantum computing especially. So what Hahn described was that you apply a pi/2 pulse and then apply a pi pulse. The signal which sort of had disappeared reappears because it was decaying not by T2 but by inhomogeneity of the magnetic field. And the inhomogeneity of the magnetic field is refocused by this pi pulse. And so you get a signal again back, and it's called an echo, a Hahn echo. You know, we call it a Hahn echo. When you use the pi pulse, called a Hahn echo. And this was a revolutionary development in the NMR. So the FID decay is dominated by B0 inhomogeneity, inhomogeneity focus in an echo experiment. The spin echo also focuses evolution due to chemical shift, as shown below. Now I have a large calculation shown here, and I'm not going to go through it. I suggest that you please, it's a very simple calculation showing that you get e to the power I h plus h prime and u plus t for tau equal to tau prime, h prime equal to 0. If they commute, then you get this evolution. Ix evolves as e to the power I h j 2 tau hz is focused. Okay, so that's the purpose. Hz is focused by the Hahn echo. Okay, I have more angular momentum evolution under J coupling. Ix1 transforms as Ix1 cos jt and 2z sin j tau I by 1. For j tau equal to pi by 2, this goes to 2iz2 I by 1. For example, what I'm saying is that you start with the Ix1, and when you come to this place, you then change this operator to 2Iy1 Iz2. Okay, and if you continue, you go to minus Ix1, and you get here, you get this is evolution under J coupling. Okay, this is the J coupling evolution operator. Okay, and you create Ix1 under J coupling, it was like this. Okay, and with this background, you can calculate all the spin dynamics of NMR. Now let me describe quantum algorithms which utilize coherent superposition. DJ and Grover search algorithm.
So
actually, I want to stop here for a minute and ask you if you have any question.
Yeah, so there is a question from Chandramani that what are the consequences if we use microwave field instead of using radio wave field?
Oh, microwave, we need a RF perturbation which is resonant with the NMR frequency. If you use microwave, it's far away.
Yes.
Okay, and that hits electron spin resonance.
Right. So for
you have to use microwave for doing resonance. For nuclear magnetic resonance, you use RF.
Right.
Is that,
if it is ESR, for ESR, microwave might be relevant. For
yes.
nuclear spin, it's only the radio frequency. The other fields, microwave will be off resonant here. Will
Yes.
not create any difference.
Yes.
Yes. Okay. I think it is answered, sir.
Okay. Now describe some algorithm which utilize coherent superposition. DJ, right to solve algorithm. There are for DJ and one qubit. There are two constant functions and two balance functions. And sorry, I'm not going to go through this here. The constant functions are that So they don't change their value, and here the interchange balance function change their value. And to calculate these things, you have to do this, and UF comes out to be like this. Okay, and 1 qubit DJ, F1S, F2S, constant balance, clean version. I think there's no, this is straightforward algebra. You just go through it. So we to do the DJ, we apply a 90-degree pulse and apply a UF. Okay, that's the bottom part of it. And all this calculation tell you that you're using control knot. You get 2 spins using transitive pulses. You get 1 line. That's a 2 qubit DJ, clean version. There are 2 constant functions and 6 balance functions. And here is the experimental result. So what you do is to DJ, you apply a pi/2 pulse and you transform. And that there are 2 balance functions and 2 constant functions for 1 qubit DJ. The 2 qubit DJ, there are 2 constant functions and 6 balance functions. So that you can verify the DJ algorithm here. This is more interesting Grover search algorithm. I have explained the Grover search algorithm in a pictorial form. There is a mathematical proof of this. And so I'm not giving you the mathematical proof. So we start with the pure state, then apply a 90-degree pulse, create equal superposition. Okay. And then we have to, somebody has to tell us which state we are searching for. So in the black box, the gentleman comes and inverts the search state. We don't know which state he has inverted. He just inverts the state. And then Grover's search algorithm says that you take invert this whole thing on the average. Take an average and invert about the average. And you get this, and repeat this operation root n times, and you get the search state with high probability. That's the Grover search algorithm. And this also has been implemented by Ranveer Das in experimental results in 1D NMR. I'm not going to tell you about the details here. They basically confirm what we did, but this is more interesting. Grover search algorithm using 2D NMR. So what do? We create a subsystem PPS, labeling of the state, computation, and reading of the state. The end result is here, that we have input state here and output state. And this is the case in which search state is 0, 0, the search state is 0, 1, the search state is 1, 0, and 1, 1. So this 2D NMR pictorially gives you the result of the Grover search algorithm in a very nice fashion. I like this more than the 1D version here. Here it's very difficult to convince you that we have done this. Okay, but here it's straightforward. Geometric quantum computing. How much time I am left with? Oh, about 25 minutes more. Okay. Geometric quantum computing. Okay, geometric phase is robust since it depends only on the solid angle enclosed by the path and is independent of the details of the path. This fact can be used to perform fault-tolerant quantum information processing. What is the geometric phase? When a vector is parallel transported on a curved surface, it acquires a phase. A part of the phase is dependent on the geometric path. Okay, so blah, 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 blah. A state in a two-level quantum system is a vector which can be transported on a block sphere. The geometrical part of the acquired phase depends on the solid angles obtained by the path at the center of the block sphere and not on the details of the path. This is a very important part. It is dependent on the solid angles obtained by the path at the center of the block sphere and not on the details of the path. If there are some fluctuations here, it won't matter. Animated geometric phase. Barry said when a quantum system prepared in one of the eigenstates in the Hamiltonian is subjected to change adiabatically, the system accumulates in the eigenstate of the instantaneous Hamiltonian and acquires a phase at the end of the cycle. The phase has two parts, dynamical phase and geometric phase. Okay, that's the dynamical phase and the geometrical phase. And total phase is given by this. Actually, Pancharatnam from Bangalore had come up with this same idea when discussing optics. And Michael Berry was very impressed by this work, and he acknowledged that Pancharatnam is actually the first person who invented the geometric phase. And he came to Bangalore, Michael Berry came to Bangalore and was looking for Pancharatnam. I don't know whether he was alive at that time or not. Non-adiabatic geometric phase. Aronoff and Anantan data showed that adiabaticity is not a necessary condition. When the density matrix corresponding to quantum state completes cyclic path in the density operator space through different intermediate states, the system acquires the same geometric phase depending upon the geometry of the path. So this non-adiabatic debate is not necessary so long as you complete the path. Okay, so we use this idea of Aronoff and Anandan to do geometric phase in our experiments. Non-adiabatic geometric phase in NMR QIQT using transition theoretic pulses. There are three people who played roles in this, that Ranveer Das, Ghosh, and Gopinath. I thought Ranveer was one of them, but I'm surprised his name doesn't appear here. Ranveer, what were you doing at that time? No? Ranveer?
I was mostly working on at that time the relaxation cross correlation. You remember the fluorine problem? The fluorine problem.
Okay, you were working on that.
Yes, and also I think also running at the moment was this parallel computation work.
Oh, correct.
So using spatial encoding, water gradient. So that's
yes.
parallel computation. Yes.
I'm not talking about that part.
Yes.
Okay. Okay, this is very interesting. So the state vector of two-level subsystems cuts a slice on the blockosphere. Suppose you come here and go up here, do a phase shift and go back. So you cut a slice in the blockosphere. The slice circuit can be achieved by two transition selective pulses, A and B. You have to phase shift them. The resulting path shows a solid angle equal to 2 phi, depending on the value of the phi. And in a spin echo experiment, we focus the evolution internal Hamiltonian. The dynamical phase is focused in this experiment. Only the geometric phase is left when we do it in this part. So so that's a great idea here. And so you can see the subtended solid angle and the geometric phase as seen in the spectrum, they match very well. Okay, so that's proof that we have the right geometric phase here. Geometric phase can be also required by a triangular circuit, which is basically half two levels of triangular path on the block sphere, and one can do that as well, and that also works quite well. Okay. Now, DJ algorithm using I can't see the top. Can you read it? DJ algorithm?
We can see the slide and it is not cut. We can see the title also, DJ algorithm using geometric phases by slice circuit.
Okay. This part is hidden by my strip here, which is telling me chat and participants and things like that. Okay. So these are these two constant functions and two balance functions. Okay, let's not go into more details. The Grover search algorithm. Now again, the very detailed work on Grover search algorithm using geometric phase. And I only want to show you the, oh no, the 2D version is not here. I think I had shown you earlier itself. This is using geometric phases. Experimental measurement of, what is it in here? Measurement of, what is written here? On the top.
Hello? Huh? Sorry?
I can't, it's hidden from me.
Okay, but here we can see everything. I mean, this is experimental measurement of mixed state geometric phase by NMR. And if you click on your slide, what happens? You can still change it.
Okay. What one does is, you have equilibrium here. You apply a small angle pulse and then apply a gradient. So you're left with a mixed state here. And in the, so after this, you get a mixed state, and you can do then geometric creation of 0 PPS, mixed state by alpha degree pulse and a gradient, and implementation of STI circuit to introduce geometric phase and measurement. So this is basically, you create controlled amount of mixed state, and then you can use that for, and here the omega is equal to 60 degrees, 90 degrees, 120 degrees, and geometric phase shift is given by this. The shift of the interference patterns function omega and r. The shift directly gives the geometric phase acquired by the spin qubit. Okay, we come to now the another interesting of the NMR QC. 15 minutes is enough. Quantum games. How many of you have played games? Quantum games, rather. You all know John Nash, his book, A Beautiful Mind, and he gave the concept of game theory, theory of games and economic behavior. There's a book by Morgenstern. John Nash gave the idea of Nash equilibrium, and he was slightly mentally deranged, and the Nobel Committee sent a person to interview him to make sure that he is fit to get the Nobel Prize, and they gave him the Nobel Prize for economics in 1994 for game theory that he developed called Nash equilibrium. He unfortunately died in a road accident on a New Jersey turnpike. This New Jersey turnpike is notoriously known for very dangerous turnpike. I have driven on it myself also. I'm sure many of you have, and I was scared. And John Nash was coming back from Europe after getting some prize, and a taxi, he was riding in a taxi, and there was an accident, and he died there at that time. Okay, he gave the idea of Nash equilibrium. Robert Aumann of the University, he gave the idea of evolutionary games. The difference between the two is that in Nash equilibrium, Nash games, the strategy is defined, is set before you start the game, and you keep the same strategy. In evolutionary games, given by Robert Aumann, you change the strategy as you play the game. You have a stationary strategy. And obviously, the gain is more in evolutionary games than in static games. Okay. We have 3 games. We implemented 3 games a week. Did that. Quantum games, guessing a number game, 3-player dilemma game, optimum strategy, going to a bar with 2 stools, battle of sexes game, should Bob and Alice together watch TV or go to a football game? I think I have only one game. Here, 2-player game. Bob thinks of a number between 1 and 2 to the power n. Alice tries to find out the number in minimum number of queries. Classically, you require n queries. Quantum, you require 1 query. Okay. So basically, is asked the question, is the first qubit one, no, one, no, yes, yes, no, yes, no. And she can tell the number. It's somewhat trivial. Total number of queries is n. But if you do a quantum version of the game, the number of queries is 1. Total number of queries is 1. So two registers, register 1 consists of n qubits, register 2 consists of 1 qubit. Alice makes a superposition of all the qubits. Bob performs unit transform and stores the result in the register B. Alice again interferes the qubits and then performs the measurement. Total number of queries 1. It's steps. In NMR, creation of PPS, application of NMR gate, unit transform of Bob, application of NMR gate, and measurement. And here is the experimental results. This molecule, 3 fluorines with very large chemical shape difference and large coupling constants. Qubit 1, qubit 2, qubit 3, this is equilibrium spectrum. Then you go to the 001 state and do you play the game? Oh, okay. So then you prepare a pseudo-pure state 001. Then this is the spectrum which is indicative of 001 pseudo-pure state. And then from there, you carry out your unity transforms and you get this result, which is equivalent to this pseudo-pure state. So guess number was 01. Okay. I used to know this. So from 001, you end up going to 011. This is the signature is 011. And so the guess number is first 2 qubits only 01. Okay, yes. There's achievements of NMR QIP. This is slightly older slide. Preparation pseudo-pure state, quantum logic gates, DG algorithm, Grover's algorithm, Hough's algorithm. I will not show you, but it's time parity algorithm, quantum games, creation of QIGZ state, entanglement transfer, quantum state tomography, limit QC, adiabatic QC, and we have done teleportation later on. Error correction we have not done, but others have done. Quantum simulation, we have not done. Quantum cloning, we have not done. Source algorithm, we have not done. And I think it was Ranveer Das who put this cup here saying NMR is the champion.
Yeah. I mean, when this 8 qubit work was done, I was there. I remember that it was very nice, figuring out the energy level diagram. You need to identify which transition is which. It was a massive work.
Well, the 8 qubit things I did not show because it is really fantastic.
Yes.
And
very big work.
In the reference to this, one can read it. And in many meetings I have shown that one, but today I did not select that because it's overwhelming. only Ranveer Das could do it. Nobody else can do it.
Right.
There are a book by Nielsen and Chuang. It's available for Indian price or this old price, 17. I don't know whether it's still available or not. I would search. I will urge all of you who are attending this meeting should buy this book. I hope it's still available. I hope it's still available for this kind of price. There was a review article by Jonathan Jones. It's also in the archive. It's published Progress in NMR spectroscopy. a large number of students. So Arvind was not my student. He was student of Professor Mukunda, but he joined a group for doing quantum computing. He was our conscious keeper. He was the theoretician who, without his saying, yes, we will not publish anything. Kavita was the one who discovered what is this called? Swap gate. And they are husband wife pair. Both went to either Mohali. Mahesh did some initial work. You remember the 2D NMR?
Sir, Arvind is now in Punjab University, no?
Sorry, I'm surprised in the last 1.5 hours my mobile did not ring.
Okay. Sir, are you saying that Arvind is in Punjab University, no?
Arvind has become the director of Punjab University?
VC of Punjab University, if I remember correctly.
Arvind has gone there.
Okay.
Vice Chancellor there.
Right.
Mahesh is either Pune, Neeraj,
Right.
Murli, I don't know. He's not in Bangalore at the moment. I don't know where he is. He's gone back to US. Maybe Das in CBS. We're talking to him right now. Rindam Ghosh in Niger. Avik Mitra was Phillips, Bangalore. Gopinath has gone to Minnesota. Now I think he has moved to what is this place called? Anu also went to Minnesota. Krishna joined Bennett University.
Achha.
We have benefit. Poor Patel is our conscious keeper. Unless he says yes, we don't publish anything.
Right.
We have collaboration from Professor Panigrahi. Non-restricted discrimination. What is that? Non-restricted discrimination? Coherent states. Or discrimination of states. He had given the theoretical idea and we did the experiment. Similarly, Arun Pati had his idea, we did the experiment. Malcolm Levitt is a giant in NMR and a good friend. Shropa Joy is now faculty at Berkeley. Joel Sen and Titi Sen are in the Charai. Lecturer dedicated to memory, Jhanarani Samal, who died suddenly, was murdered in 2009 by a deranged person. She left, she had finished 5 years. She had left enough material for the thesis and three, 4 papers that were published afterwards. One of them in PRL, which is, I think, it was Arun Pati's idea of no hiding theorem that she verified by NMR, given PRL. Thank you very much.
Thank you, sir. And the session is now open for question.
Yeah, thank you, Professor Anil Kumar. Excellent talk. Really enjoyed it.
Yes. Sir, there is a comment, there is a request rather. Ms. Lydia Fernandez is requesting, can you share the book slide? That slide, can you show once more? The books where you recommended Nielsen Chuang's book and Jones' book. It's going back.
Pseudo-Pure State.
The book slide. The book slide means where you showed the Nielsen and Chuang's book, and also towards the end, just before.
Okay. Books.
Yes.
Yeah,
Yeah, this.
Jonathan Jones.
Yes. So they can take a note of it, the archive numbers and.
Correct. Yes.
Okay.
I don't know whether the price has increased or decreased. 317.
The price probably it's still around that 3 to 400. I mean,
Okay.
it has not changed much. Not changed much. Okay. Okay. So Aniruddha Sharma, he mentioned it's around 600 on Amazon.
Okay.
The price of this book. Okay. And it was very nice. I mean, every time I go through this, I remember that early 2000, our
This is not
lab
just
productivity
this
was
book is not
phenomenal.
for this book is not for NMR. It's a general book on quantum computation, quantum information process.
Right.
The Jonathan Jones article and book are on NMR.
Right. The next one. Yes. Yeah. So I was saying early 2000, I mean 2000 to 2010, our group's work on quantum computation, I mean that reached a very feverish pitch. It was very productive period.
Yes. We published about 40 papers and graduated 8 students for PhD.
Right. It was super. I mean, I left when Ovik started his works on quantum games.
Yeah.
It's very nice. So any other question we have from the audience? Professor Anil Kumar would be very happy to answer if you have questions. And we still have a couple of minutes left. Sir, I have a question.
Yes.
This geometric phase, I mean, what you showed is basically, it looked like, if I understood correctly, it's for a single spin. It was moving on it was made to move on block sphere.
Yes.
And depending on how much solid angle it covers,
Yes.
the geometric phase would be proportional to solid angle, as we all know.
Correct.
Now, if we have a multi-spin system and we create an entanglement, and suppose we make it evolve, obviously block sphere representation will not work. One has to work on a hypersphere or abstract calculation. I mean, we bring the entanglement exactly back to where it was. Suppose we make an evolution of that kind. Will we still have a proper geometric phase for that entanglement?
If it is entangled state.
Yes.
I don't know. If you start with the entangled state, whether you perform geometric phase on one of the spins, actually in the entangled state, the spin is not a good quantum number.
That is true.
You may not be able to perform operation on a single spin of entangled system.
That is true. So I was thinking, I mean, more like for a 2-spin system, one can work in the triplet and singlet basis. So suppose we are in the triplet basis.
That will work.
That will work.
That will work because they are independent spaces.
Right,
Singlet and triplet states are independent spaces.
Right.
That will work.
So in triplet basis, one can create entangled state and move it around in the triplet basis and bring it back where it was, and maybe it will have a geometric phase.
It's an interesting idea. It's an interesting idea.
Right. So there is another request. Please share the game theory slide. If you can show that slide, basically they are.
This has been recorded. This lecture has been recorded, and I have no reservation that if whole lecture is given to every participant.
Oh, that is wonderful. That is wonderful.
Please spread it to everybody. You give this, like I send it to you, you can give it to all the participants.
Okay. Okay.
I have no reservation.
They would be very, very, very happy.
Yes, yes, please share this, all the slides to all the participants, whosoever wants.
Right. So we have one more question came in.
Yes.
The question is, to perform the operation, by operation it is meant the elemental gate operation, I guess.
Yes.
Only the RF pulses are controlled, or the magnetic field is also changed?
No, no, magnetic field is not changed. You only use the RF pulses and evolution as controlling things. The J evolution can be focused, not focused, and RF pulses can be applied at various angles.
Right.
So these are the only two parameters we have to play with. To focus a certain part of the Hamiltonian, use the spin echo. We can selectively focus certain parts of the Hamiltonian and not and let the other part evolve. Provided they are weakly coupled. If they're strongly coupled, then there is a problem.
Right. Sir, we have one more question. The question is, I mean, like a quantum computer, if it is based on liquid streams, then how would you store it? In the sense, the classical computers are in solid state. We do not have a problem handling them, storing them. And if it is based on liquid, NMR quantum computer, if you have a comment on that.
You need to go to the spectrometer. Spectrometer cannot compete. That's the NMR. But let me tell you something. For example, this quantum computers made by IBM and other people, Google, they give you access to some of them free of cost. There's in your institute, there's this gentleman called, he's published perhaps 50 papers so far on using the IBM quantum computer. What is his name?
Vikas Behra.
Vikas Behra.
Yeah.
Yeah. Fantastic. It's all sitting in Calcutta. He doesn't have to go to IBM lab in Murray Hill. They give access. Right. Now, Google is also, I think, giving access to the quantum free of cost.
Correct. One has to submit a proposal. As long as it's a reasonable one, their experiments will be done.
Yes. Earlier, you didn't have to even give a proposal, just use it. But now I think they have come to a point where maybe they need to first accept your proposal.
Right.
They want to make sure that you don't misuse it. You only use it for academic purposes and not sell further. You're not making money out of it.
Right. Okay. Any other question from the audience? If not, then we already spent, I think, 1.5 hours, and Professor Anil Kumar, despite his old age, I mean, he's still so active and spent so much time with us. It was a wonderful lecture. He answered the questions, and it's very enjoyable, sir. And thank you very much.
Yeah, really, thank you, Professor Anil Kumar. I did enjoy it. Every time I listen to you, get some ideas.
Wonderful. It's nice talking to you, Prashant.
Yeah.
And,
Same here. Thank you. You know, Professor Anil Kumar, we have made Manu agree to give a talk. You know, he's now with Cadila Healthcare, Vice President there.